Hello and welcome to the fourth lesson on exponentials and logarithms for the Year 12 and AS course. So you should have watched the previous 3 videos and done the previous 3 lessons. This time we're going to have a look at how exponentials and logarithms actually work and relate to each other. First of all though, as ever, there's a warm-up. Here's 4 warm-up questions for you to try. Pause the video here, try the questions yourselves. When you're ready to see the answers, press play. Okay, so here are the answers, starting off with question 1. Estimate the solution to the following equation using the graph provided, 3 to the power x equals 4. And so we're wanting to find out what value of x would give us a y coordinate of 4. So the most obvious thing to do here would obviously be to just draw a straight line across the graph at y equals 4 and estimate from there. So if I draw a line across, then where it intersects the curve, go down, and we can see that the value you're after is between 1 and 1.5. So if you've got good eyesight, maybe better than mine, you can see that each one of these little rectangles going across must be 0.1. So 1.1, 1.2, that's 1.3. That seems to me to be about 1.3ish. And so my estimate would be that x equals 1.3. But let's see if we can improve on this in question 2. So question 2, we're using trial and improvement to estimate the solution to the equation 3 to the power x equals 4, as we did in question 1. But now, rather than using a graph, we're going back to GCSE and doing trial and improvement. Give your answer to 2 decimal places. So we've kindly been given 1.2 is 3.73719, which is obviously too small. So my suggestion would be to just take this up to maybe 1.21 and see what happens there. So when x is 1.21, 3 to the power 1.21 we can calculate. Let's move the calculator along. So 3 to the power 1.21, get 3.778ish. So that's obviously still too small. So let's keep going up and see what happens. We'll eventually get to 4 or over. So go to 1.22, 3.820. Again, still too small. Now you could skip ahead and try 1.25 or something, but I always just do it step by step, which sometimes infuriates my students. Because I'm quite close, I think I can just do it step by step. Anyway, 1.23, going up the other step. 1.23 would give us 3.862 to 3 decimal places, which again is obviously too small. .24. Not the most exciting method is trial and improvement, but it does work. 3.905, so we're definitely getting closer. 3.905, still too small. .25. .948. Too small again. 1.26. Now that's looking very good, isn't it? 3.992, but it's still too low. Now with trial and improvement, no matter how tempting it is, we need to look for a change of sign, where our estimate goes from below the needed solution to above it. So we need to try 1.27. 1.27 is going to give us an answer of 4.036, which is obviously too high. Now I've got a change of sign between these two values. What we need to do is try halfway between 1.26 and 1.27, and this will be our final trial. If this is too high, then 1.26 is our solution. If this is too low, 1.27 will be our solution. So this here is the acid test. This is going to tell us if it's 1.26 or 1.27. 3 to the power 1.265 gives us a value which is too high. That's 4.0138. So about 0.14, which is obviously too high. So therefore, the nearest value to 2 decimal places is 1.26. So x must equal 1.26 to 2 decimal places. The whole point of warm-up question 1 and 2 is just showing you what an absolute pain in the backside it would be to have to work out these equations using these methods. Is there a quicker, nicer way of working out equations where we've got an unknown in the exponent? This is the point of this lesson. The good answer is yes, there is an answer to this to make it much easier. You don't have to do a graph and trial and improvement all the time to solve these equations. Anyway, question 3, solve these. And so if you notice here, 2 to the power of 3x equals 64. 64 itself is a power of 2. So what we can do here is rewrite 64 as a power of 2. It's 2 to the power of 6. And we've also been told it's the same as 2 to the power of 3x. So therefore, from this, what we can deduce is that the powers must be the same. So 6 must equal 3x. So x must equal 2. We can use the same idea here, because 729 is again a power of 3. It begs the question, what if 729 wasn't a power of 3, which is the same as what I said in warm-up question 2. That is another method we're going to explore today. Anyway, 729 is, if you want to try the calculator you can, it's 3 to the power 6. And 729 we're told is also this. 2x minus 1. So in the same way as part A, pardon me, in the same way as part A, we can now equate these exponents. So therefore 6 must be the same as 2x minus 1. A simple rearrangement of this equation, add 1 to both sides, divide by 2, we get that x must be 7 over 2. Finally, question C. Again, 64 is a power of 4. 1 over 64 is the same as 64. Whoops, what am I thinking? So it's almost like I'm half asleep today. So 64 is the same as 4 to the power 3. So 1 over 64 is the same as 4 to the power minus 3. So this is the same as 4 to the power minus 3, but we're also been told it's the same as this. Making a real pig's ear of this, aren't I? Sorry. So that's the same as 1 minus 0.5 to the power x. So all I've done here is put 1 over 64 as this. And because the bases are the same, in the same way as part A and B, we can equate the exponents. So in the same way, we can now say that therefore minus 3 equals 1 minus 0.5x. We can double both sides now. So minus 6 equals 2 minus x. Then rearrange quite easily, add x to both sides and add a 6 to both sides. We get that x must equal 8. Warm-up question 4, Calculus Corner. We've got this radioactive decay of a substance and can be modelled using an equation which is exponential decay using E, which lots of decay questions can be. So R is the amount of substance remaining, and R0 is a half-life of a substance which remains constant. If you're wanting to know, the half-life of a substance is the amount of time taken for the mass of a substance to half through the decay process. Anyway, that's a little aside for you, ask your physics teacher. T is the time in years. So you've got all this explanation, but actually the question just boils down to find dr by dt, differentiate r with respect to t. So all we need to do actually, that's just a bit of colour to it, is to do dr by dt. So from last lesson, you should remember that when we differentiate a exponential, where it's to the power e, any constant before the variable gets brought down to the front and multiplies any coefficient before the e. So we just bring down this minus 0.0125 and make it multiply r0. And so this just becomes minus 0.0125 multiplied by r0, and then e to the power minus 0.0125t. And that's all we need to do. So the main bit of this lesson is logarithms and how they link to exponentials. So let's start off by explaining. Let's think about the equation y equals 2 to the power of x. So how could we solve this? Obviously, using question 1 and question 2 from the warm-up as an example, we could do a graph and estimate the value of x needed by drawing a horizontal line at y equals the known value, or we could do trial and error. Another way we could do it would be to just make x a subject and then plug in what we need for y. So could we make x a subject of this? Well, we can't with what we know so far in maths, so we need something else to make x a subject. So there is an inverse function to exponentials and powers, and these are called logarithms. So any relationship that can be represented as an exponent, as a power, can also be represented as a logarithm. So if you've got something which is a to the power x equals n, that's one and the same thing. It's equivalent to saying that's log, which is short for logarithm, to the base a, n, equals x. But a can't be 1. I'm going to explain what this means in a bit more of a simple way for you. So if we take a familiar example, this will just add a bit more colour and make it easier. And in fact, if you ever get confused by logs, remember this example, because you know it to be true. Think about a to the power of x equals n for something easy, like a power 10, and the power being 3. 10 cubed equals 1,000. So I've just said a is 10, x is 3, n is 1,000. So from the above, if we just rearrange that, we can say that log base 10 to the power 1,000 equals 3. So looking at this, it's now easier to see how these numbers relate to each other. So have a look how the 10, 1,000 and 3 relate. So I'm going to explain it now. Here's how I think of it. So put simply, the log of this number n here is the power to which a needs to be raised to equal n. So in our case here, what power does 10 have to be raised to make 1,000? Well, 10 has to be raised to the power 3 because 10 cubed would give us 1,000. This is why the answer to this is 3. So this is one way you can think of logs. The log of a number, in this case 1,000, is a power to which you need to raise the base to get that number. So let's have a look at some examples. So rewrite each of these statements as a logarithm. So first of all, question A. Oops, I'll get a different colour, don't want to be in red. So for A, 3 to the power x equals 4. I just write this up from before, so you can use this as a guideline, should you get confused with this abstract algebra. And also we knew that 10 cubed is 1,000. So looking here, the base is always the same as the base of the power. So it's going to be log base 3. If you look here, the power goes to the end of the equals, and the answer to the power we put inside the log. And so here the answer to this is 4. and then we have an x, like so. Okay, what I might actually do for you is colour code these numbers for the example we know to be true. You can see how these numbers are swapping round to help you. Okay, so this might seem like a bit of a silly thing to do, but it will hopefully help you to see what's happening in terms of how these numbers are switching. Let's try this method for b. So if you've got b here, let's colour code them again. And so this time our base is 3, our power is 4, and our answer is x. So what happens here is for log, we put the yellow thing first, which is 3. The base of a log is always a base of a power. And then we put the blue after the base, so the blue here is the x. And for green here is a 4. So we put log base 3 to the x equals 4. And then for c, exactly the same idea, only this time it's just been written back to front. So we've got the base, which is x this time, the power, which is a 4, and the number which isn't anything to do with the power, which in this case is 3. So in the same way we can rearrange this. So it's going to be log to the base x. The next number we're going to put down is going to be the 3, and that's going to equal 4. And so that's how we do these. Work example 2, write each logarithm as an exponential statement. So if we just think about what we had before, and always remember something like this, because it just makes it more obvious. The log of a number is a power to which we raise the base to get that number. We need to raise 1,000 to the power, so we need to raise 10 to the power 3 to get 1,000. So always remember, something like this would be my suggestion, until it becomes more second nature, then you wouldn't need to. So this one here, log base 2 of 8 is 3. And so like I said here, 10 to the power 3 is 1,000. And so these two numbers link to make this one. And so if you notice here, 2 to the power 3 equals 8. As simple as that. This number to the power that number has to equal this number. That's just a different way of how we can rearrange the log. Over here, using the same idea with part B, 2 to the power minus 2 equals a quarter. And finally for C, 9 to the power 3 over 2 equals 27. If you doubt this, just try it with your calculator. So worked examples, question 1 and question 2, I'm just trying to show you how these numbers in the logs work and how they relate to one another. Question 3, without using a calculator, find these values. Like I said before, the log of a number is a power to which we need to raise the base to get that number. And so what power do we need to raise 5 to get 125? Well, that's going to be 5 to the power 3. And so the answer to this one is 3. So for A, the log base 5 of 125 has to be 3. For part B, what power of 2 do we need to get 1/16? Well, hopefully you'll see that 1 over 16 is the same as 2 to the power minus 4. 2 to the power 4 is 16, so 2 to the power minus 4 is 1 over 16. So we need to raise 1 over 16 to the power minus 4. And so log base 2 to 1 over 16, we need to raise for 2 to the minus 4. And for C, what power do we need to raise 10 to get 0.1? Well, 0.1 equals 1 over 10, which is obviously 10 to the power minus 1. So we need to raise 10 to the power minus 1. So log base 10 of 0.1, that just equals minus 1. Some final worked examples to have a look at here. So again, what I'm going to suggest we do is we refer back to the idea of 10 cubed equals 1,000, just to make this a bit simpler. So I've got this here. So here, the unknown number for the first one is the number after the log. And so we want to work out what 1,000 would be. So how do these two numbers relate to the middle one? And so obviously you can see here from a real example, 10 cubed equals 1,000. And so this number here is given by taking this number here and raising it to this power. So using this idea here, we can hopefully now see that x must be 5 to the power minus 1, in the same way that 1,000 is 10 to the power 3. And 5 to the power minus 1 is obviously 1/5. For b, again we can use the same idea. We still need to find x, which is in the same place. And so x is going to be 343 raised to the power 2/3. So if you remember laws of logs, what we're going to have here is the cube root of 243 squared. Of course you can just use a calculator, but I think this is a good opportunity to just remember what's happening with laws of indices and surds. The cube root of 343 is 7, and then 7 squared is 49. And so x would have to be 49. And for part C, again we can use this idea here to see how these relate. And so how can we get 10 from 1,003? Well, hopefully you can see here that 10 is 1,000 to the third root. The cube root of 1,000 gives us 10. So the same way here, we can see that x must be the cube root of 64, which is 4. A different way we could have used is to have thought x cubed must be 64. So x equals 4. That's just a different way of doing it, which we could have used. So anyway, you need to try these yourselves now. So if you could please go to page 320, exercise 14D, and try those questions yourselves. Use the back of the book to self-assess. If you got them wrong, try again. If you're still not sure, do ask me or get in touch in the comments section. I don't think enough of you are doing that already, if I'm honest. So carry on working hard, keep pushing on, and you'll hear from me next in the future videos. Thanks for listening.